Swayam Prabha. Digital India. Educated India.
Dear students, I welcome you all in the fifth lecture under crystallography here. And in this lecture, I will discuss the fundamental basis of classification of crystal systems here. Now, if you want to know this fundamental basis of classification, we need to know three aspects of it. Three aspects, namely, what is crystallographic axis? We need to know what are the choice, and what is about the unit cell lengths, that is we tell it in terms of A, B and C, and what is the angle between this axis here, which is called as interaxial angle. So, A angle B, this is denoted by the symbol gamma, B angle C is denoted by the symbol alpha, and A angle C, this is denoted by the symbol beta. Excepting crystals belonging to triclinic, belonging to trigonal and hexagonal crystal system, where there are 4 crystallographic axes. In crystals belonging in the remaining 5 crystal systems belonging to triclinic, monoclinic, orthorhombic and say tetragonal crystal system here, and also in isometric. In this 5 crystal system, there are 3 crystallographic axes. Now, in general, if we denote this 3 crystallographic axes by the symbol A, B and C, the A axis, the general convention is that A axis will be pointed towards you, that the positive direction of A crystallographic axis will be pointed towards you, whereas the B crystallographic axis will be sideways and the right side will be the positive direction of B crystallographic axis, and this is the C crystallographic axis. This is the vertical crystallographic axis, is the C axis, this is the positive direction of C, and the C angle B, this is alpha, A angle B, that is gamma, and A angle C, this is beta. In case of crystals belonging to hexagonal and trigonal crystal system, there are 4 axes. The axis which is vertically oriented, we call it as C crystallographic axis, whereas the axis which lie in the horizontal plane, these axes are called A1 axis, A2 axis and A3 axis. A1 is pointed towards you, pointed towards us. So, this is the positive direction, A2 is the positive direction of A2 is here, and this is the positive direction of A3 axis here. And the angle between the 3 horizontal A1 and A2 and A3 axis, this is 120 degree, and the angle between C axis and any one of A1, A2 and A3, this is 90 degree. With this basic understanding, let us study in some more details what is a crystallographic axis. Generally, as I have told you, they are 3 in number, occasionally 4, as we have seen in case of minerals belonging to trigonal and hexagonal crystal system. They are mutually perpendicular if possible. Thirdly, they should coincide with the crystal symmetry axis. If in a particular crystal symmetry axis are present, so for example, if there is a 2-fold axis of symmetry or a 3-fold axis of symmetry or a combination of this symmetry axis, it is the preference is that the crystallographic axis should coincide with the symmetry axis. If the symmetry axis are lacking or sufficient number of symmetry axis are lacking or symmetry axis is not present, then the normal to the mirror plane that is present, that will be oriented as one crystallographic axis. In case of certain crystals belonging to certain crystal system, they lack sufficient symmetry axis or planes. In those cases, the axes are selected to coincide with the lines of intersection between faces of greatest area. So, those faces which have the largest area, their intersection is a line, and that line is taken as one of the crystallographic axes. Let us start with a triclinic crystal system, and in this crystal system there are two crystal classes are allocated. One is called 1 and the other is called bar 1. And what is the meaning of this triclinic? Tri means 3, clinic comes from inclined. That means, all the 3 crystallographic axes, all the 3 axes are inclined. What does it mean? It means that in this case alpha is not equal to beta, is not equal to gamma, is not equal to 90 degree. And also A is not equal to B, is not equal to C. Now, if you consider among 1 and bar 1 has more symmetry than 1. So, in general, in triclinic system, bar 1 we will learn later that this is called a pinacoidal class, and there is the presence of a center of symmetry here. And let us consider that this face here. So, this is the bar 1 axis here. So, this is this face here and this face here, they are related to each other by the presence of a center of symmetry. In the similar way, this triangle and this triangle here can be related to each other by the presence of the center of symmetry or operation of inversion. Now, this is where you can see that this axis, the intersection of this face and this face is one axis here, the intersection of this face and this face is another axis here, and intersection of this face and this face is So, these are essentially you have the 3 axes here A, B, C. Importantly, the angle between this axis is never 90 degree, and also the cell dimension is unequal. What are the minerals which show generally this pinacoidal class or which comes under the triclinic crystal system? One is microcline, which is shown here, and it is also present in plagioclase, turquoise, and also in wollastonite. Now, let us come to this crystal system called monoclinic, and under this crystal system there are 3 crystal classes here, 2, M and 2 over M. And what this monoclinic means? Mono means 1, clinic means inclined. So, among the 3 crystallographic axes, one of the axis is inclined. What does it mean? It means that among alpha, beta and gamma, alpha and gamma they are equal and they are equal to 90 degree, whereas beta is not equal to 90 degree and A is not equal to B, is not equal to C. Now, let us try to understand with respect to these 3 sketches here. In case of monoclinic crystal system, if you have a two-fold axisosymmetry like this, so you have the 3 crystallographic axes A, B and C. B axis coincides with the two-fold axisosymmetry. That is why this two-fold diet symbol is here. So, this is the line, this is a two-fold axisosymmetry and this is your B crystallographic axis here. And if this is a two-fold axisosymmetry perpendicular to this two-fold axisosymmetry or perpendicular to B, you can take a plane, this plane here. In this plane, A and C crystallographic axis will lie, and the A angle C, that is your beta, that is not equal to 90 degree here. So, in case of the point group of symmetry 2, this is the orientation of crystallographic axis and with its relation with the symmetry elements here. If you have a mirror plane only M and it lacks a crystallographic axis, what happens? So, in the mirror plane, if this is a mirror plane, you take an perpendicular to this mirror plane, and that perpendicular is your B crystallographic axis. Immediately you know that in this plane, in this mirror plane, A and C crystallographic axis will occur, and the angle between A and C, as we have seen here, is beta is not equal to 90 degree, but C angle B, A angle B is 90 degree here. And in the normal class of the monoclinic crystal system, that is 2 over m, what you have here? You have both a two-fold axis symmetry and you have a perpendicular mirror plane. So, in this case, this two-fold axis of symmetry is your B crystallographic axis, and in this mirror plane A and C occurs, and A angle C, as I have told you, that is beta is not equal to 90 degree here. So, what are the common minerals showing monoclinic system or occurs in monoclinic system? Particularly, if we talk about the normal class of the monoclinic system 2 over m, they are micas, for example, biotite and muscovite, and you also have azurite, chlorite, clinopyroxene, epidote, gypsum, malachite, kaolinite, orthoclase and talc. They all show this symmetry of 2 over m. And this is a diagrammatic sketch of a crystal showing this symmetry 2 over m here, or the crystal class 2 over m. You can see that the different crystal faces are shown here, and this is your two-fold axis symmetry, which is your B crystallographic axis, and in the perpendicular this is your mirror plane. In this mirror plane you will have the A crystallographic axis and you have the C crystallographic axis, and that angle is beta is not equal to 90 degree. Now, this is essentially in some details these two crystals which I am showing you here. This is a triclinic crystal and this is a monoclinic crystal, and the crystallographic axis have been shown as A pointed towards you, positive direction. This is B sidewise positive, and this is the positive of C, and this is the vertical here in this vertical direction, and as I have shown you here, A angle B angle C is not equal to 90 degree, and they are also unequal in length. Whereas, in case of monoclinic crystal system, as I have shown you here, so this blue colored face, this is parallel to the mirror plane, and orthogonal to it you have this B crystallographic axis here, and your mirror plane is this one here. So, in that mirror plane you will have A and C here. So, remaining C vertical, A is slightly inclined, so that A angle C is not equal to 90 degree here. Now, let us come to the orthorhombic crystal system here. In the orthorhombic crystal system, you have three crystal classes here. These are 2 to 2, 2 mm and 2 over m, 2 over m, 2 over m. So, let us see what we have in 2 mm. 2 is your vertical crystallographic axis. So, this is the direction, that is your vertical two-fold axis symmetry, which coincides with the C crystallographic axis here. And you have the two vertical mirror planes, one of this orientation here, another mirror plane of this orientation here. So, if you take a direction orthogonally to this mirror plane, so this will be your A crystallographic axis, whereas in this mirror plane will lie B crystallographic axis and C crystallographic axis. Whereas, in this particular mirror plane, if you take a perpendicular to this mirror plane here, this will be your B direction here, and in this mirror plane we will have C crystallographic axis and A crystallographic axis, and the angle between A, B and C, alpha, beta and gamma, they are all 90 degree. This is your 2 mm. What you have in case of 2 to 2? So, you now remember when we write 2 to 2, there are three two-fold axis symmetry, one is vertical and the other two are horizontal. So, in this case the crystallographic axis are said to coincide with this three two-fold axis symmetry, one of vertical orientation and the other two are of horizontal orientation here. So, this two-fold axis or dyad is the position of A crystallographic axis, This will be the position of B crystallographic axis with this diode it coincides, and with this direction of diode C crystallographic axis coincides here. And in case of the normal crystal class of the monoclinic crystal system, in this particular case you have 3 two-fold axial symmetry like this orientation, and this orientation, and perpendicular to it. So, if you have C crystallographic axis and if you have a two-fold axis of symmetry oriented along this, it coincides with this in the perpendicular to it. This is blue plane, this is perpendicular to the vertical two-fold axis symmetry, which is also the C crystallographic axis. And with respect to this horizontal two-fold axis, this green plane is the mirror plane or vertical mirror plane here, whereas with respect to this diode, this particular plane is perpendicular to it here. So, in this case of normal class of the orthorhombic crystal system, you have the axis ABC coincides with the 3 diodes and is also orthogonal to the 3 mirror planes there. So, this is called rhombic dipyramidal class here, and we have already studied. I have repeated here, there are 3 two-fold axial symmetry, 3 mirror planes, and there is also a center of symmetry here. What are the common minerals? They are andalusite, anthophyllite, aragonite, barite, cordierite, olivine, sillimanite, stibnite, sulfur and topaz. And this particular part also I have repeated. Ortho means orthogonal, that means all the 3 axes are at of 90 degree. So, alpha, beta is equal to gamma is equal to 90 degree, and A is not equal to B is not equal to C. One of the reason why this is so, even in 2 over m, 2 over m, 2 over m, because the angular orientation is 90 degree and the repeat angle of each axis is, say for example, 180 degree. So, each axis is not equivalent, they are non-equivalent axes, that is why their unit cell length are different. Now, let us come to the tetragonal crystal system here. So, in case of tetragonal crystal system, what you have here? What are the crystal classes that are come under this? They are 4-fold axial symmetry, bar 4, 4 over m, 422, 4 mm, bar 4 m2 and 4 over m, 2 over m, 2 over m. What is the minimum criteria for a tetragonal crystal system? So, you have at least you have one tetrad or bar 4 axis, that is the minimum criterion you have. This the number of 4-fold or bar 4 axis, this should be only one, it should not be more than one. There are 3 axes here. C axis is vertical parallel to the A4 or 4-fold axial symmetry or bar 4, whereas in the horizontal plane we lie 2 axes which is marked as A or B, but since A is equal to B, we give a nomenclature of A1 and A2, and the angle between C crystallographic axis and A1 and A2, this is 90 degree here. C angle A1, C angle A2 and A1 angle A2 is 90 degree, whereas C is not equal to A1, A1 is equal to A2. I will explain why this constraint or this restriction comes about. Let us talk about this 4-fold axial symmetry. You must be aware of this drawing which we have done it before. So, this is your vertical 4-fold axial symmetry here. So, what you have here? So, this is this C crystallographic axis is parallel to the 4-fold axial symmetry, or C crystallographic axis coincides with the tetrad. So, immediately you know that in the you can take a plane perpendicular to the tetrad, that is your horizontal plane, you can have 2 axes here, A1 and A2. So, if you take this as A1, then since your vertical axis is 4-fold, so the repeat angle is 90 degree. So, A1 can be rotated and made parallel to a direction which I have marked it as A2. Now, because these two axes are related to each other by the rotation of vertical fourfold axisymmetry. So, atomic distribution along these two directions are the same, atomic density is the same, atomic distribution is the same. That is why unit cell length along A1 direction and along A2 direction, this is the same. That is why you have A1 is equal to A2, and A1 angle A2 is 90 degree and C is vertical. So, C angle A1 and C angle A2 is equal to 90 degree, as I have written here. So, this particular feature can be repeated in all these crystal classes, the drawing that I have made here. So, I give you a few other examples and the others you can try on your own. So, let us consider this 4 mm here. So, in this case your fourfold axis, your vertical C crystallographic axis, that is why C is written at the center, and you have these 4 mirror planes that have been drawn here, and you can immediately find out here that with respect to one set of mirror plane like this, you can draw a perpendicular to it, that is this direction here, you can call it as A1, and with respect to this vertical mirror plane, you draw a perpendicular to it, it becomes A2, and as I told you here that this is a vertical fourfold axis. So, this direction can be rotated 90 degree and will make it coincide with the direction of A2. So, A1 and A2 are equivalent directions and their unit cell length will be the same. So, this you can repeat it with all the crystallographic axes. So, that you have this unique situation here, where you have in the horizontal plane you have A1 and A2 are present, they are equal in lengths, their angular orientation is 90 degree, and it also makes a 90 degree angle with a vertical direction, that is your C crystallographic axis, and C is not equal to A1, A1 is equal to A2. Why C and A1 are not equal? Essentially because you can do it with this particular one here. If we talk about this 4-2-2 business here, so you have the vertical fourfold axis symmetry and you have the horizontal twofold axis here. So, what will happen here is that this horizontal twofold axis cannot rotate this twofold axis and make it coincide with this vertical fourfold axis, because its repeat angle is 180 degree. So, if it is this particular direction is rotated 180 degree, this will coincide with this. So, it will not coincide with the vertical fourfold axis symmetry. That is why C crystallographic axis and A1 direction, C crystallographic axis and A2 direction, they are non-equivalent directions here. Okay. Let us give an example with respect to a crystal, how the for a particular point group of symmetry like 4 over m, how the crystallographic axis is there. So, this is in case of 4 over m, you can immediately understand this is your vertical fourfold axis symmetry and this is a horizontal mirror plane of this orientation here. So, there are pyramidal faces here. So, one pyramidal face is here, another pyramidal face here, and there are two on the opposite sides here. So, all these pyramidal faces can be related to each other by rotation of say 90 degree here. So, the examples of minerals which come under 4 over m are scheelite and scapolite. So, these two minerals having crystallized under the 4 over m crystal class. Now, if we show the orientation of the axis in this two crystal system that we have learned now, orthorhombic and tetragonal. So, this is your, if these are the different crystal faces that have been shown in this orthorhombic crystal system. So, this is your A direction, A is perpendicular to this crystal face that has been shown here, B is perpendicular to this crystal face here, and C is perpendicular to this crystal face here. And you have already seen, if it is for 2 over m, 2 over m, 2 over m. So, then all these crystal faces, this one and this one will be a mirror plane here. So, you can have different ways you can think of this orthorhombic crystal system. One of this type you see here, the another type here, where the length of the C crystallographic axis is less than A and B dimensions here. So, this particular vertical length is much smaller, and in some cases the A crystallographic axis is not perpendicular to a crystal face. So, it passes through the intersection of these two faces. So, it passes through the midpoint of that. And the same thing, you have a tetragonal crystal system here. In this case, this is your vertical C-fold axisymmetry, and you have A 1 here and A 2 here, and A 1 and A 2 is perpendicular to this crystal face shown as the green colored face here. They are equivalent faces, because C coincides with a tetrad axis here, tetrad, which is a fourfold axisymmetry, and that is why 90-degree rotation will make this face coincide with this. This will be equivalent face, and also the crystallographic axis A 1 and A 2 are equivalent. And in this case, A 1 and A 2 are not oriented perpendicular to the crystal face, but they passes through the center of the edge formed between the intersection of the faces here. So, these are the orientations of crystallographic axis in orthorhombic and tetragonal crystal system here. Now, let us come to the trigonal crystal system. Under this crystal system, you have 3 bar 3, 3 over m, you have 3 2, 3 m and bar 3 2 over m. What is the minimum criterion? The minimum criterion is the presence of a triad or a bar 3 axis. So, in this case there will be 4 crystallographic axes. C axis will be vertical and in the horizontal plane, and what you have here, and along this C you will have either a triad or a bar 3 axis, and in the horizontal plane you will have 3 crystallographic axes. They are A 1, A 2 and A 3, and C angle A 1, C angle A 2 and C angle A 3 is 90 degree, and A 1 angle A 2 angle A 3 is 120 degree, and C is not equal to A 1, but A 1 is equal to A 2 is equal to A 3. And I have drawn this projections here in this all these different crystal classes under this trigonal system here, and each case I have marked the position of A 1, A 2 and A 3 axis and also the C crystallographic axis. I give this I show this orientation of this axis with a few examples here. Let us start with this very simple crystal class, which is 3. What you have here in 3? So, your vertical axis is your C crystallographic axis, and this is your C crystallographic, it coincides with the threefold axisymmetry, and you have to take a plane perpendicular to the C crystallographic axis, that will be this horizontal plane and this circle that is shown here. So, in this horizontal plane, let us consider this direction here, let us mark this as A 1 direction here. So, since you have a triad here, the vertical. So, repeat angle is 120 degree. So, 120 degree rotation will make A 1 coincide with a direction. Let us consider this direction is A 2 direction, and another 120 degree rotation will produce another direction here, we call it say A 3 direction here, and another 120 degree rotation A 3 will coincide with A 1. So, in this horizontal plane you now can consider 3 crystallographic axes, one of this orientation A 1, the other of this orientation is A 2, and this one is the orientation A 3. And because they are related to each other by 120 degree rotation, they are all equivalent axes. And as we have seen in case of tetragonal crystal system, atomic density or concentration of the atoms along A 1, along A 2, along A 3, this will be the same. That is why unit cell dimension of A 1, A 2 and A 3 is same, but this is non-equal to the vertical C crystallographic axis. Why? We can think of with respect to this crystal class here, say for example 3,2. What we have in 3,2? This is your vertical C crystallographic axis, C is shown to lie at the center, and the 3 horizontal crystallographic axis, they coincide with the 3 horizontal two-fold axisymmetry. A1 coincides with this two-fold axisymmetry, A2 coincides with this two-fold axisymmetry, and A3 coincides with this two-fold axisymmetry. So, as I have told you that the triad operation makes this A1, A2 and A3 as equivalent. But if you want to link the one of the horizontal axis here, say for example, A2 axis by the operation of say this two-fold axis symmetry, this A1 two-fold axis, A2 will never coincide with the C crystallographic axis. That is why C and A1 are not equivalent directions here. That is why C is not equal to A1. So, with this we can go to the next crystal system, which is hexagonal crystal system, and as you will find out that both in trigonal and hexagonal system, this is broadly the same, particularly crystallographic axis and their interaxial angles and unit cell length, they are broadly the same. But what is the minimum criterion for an hexagonal crystal system? You have to have one hexad or a bar 6 axis, and as before in trigonal crystal system, you have 4 axes of symmetry here. The C axis is vertical and will be parallel to the vertical 6-fold axisymmetry or bar 6 axisymmetry, and in the horizontal plane there will be 3 crystallographic axes named as A1, A2 and A3, and the C angle A1, C angle A2, C angle A3 is 90 degree, whereas A1 angle A2 angle A3 is equal to 120 degree, and C is not equal to A1 is equal to A2 is equal to A3. So, I can again explain this relationship using first with this 6-fold axis of rotation with this point group symmetry here. So, this is your C crystallographic axis orientation, this is your 6-fold axis of symmetry which is vertical. So, in the horizontal plane you can think of one direction here, that is A1. So, if you rotate 60 degree, A1 comes to this direction here, another 60 degree, this direction comes to this direction, which I call it as 60 degree here as A2 direction here. Another 60 degree rotation, A2 comes and coincides with this direction here, that is your A1 direction. Another 60 degree rotation, this direction now coincides with A3. So, these directions, this is the negative direction, this is the positive direction of A3. So, essentially you have the A1, A2 and A3 axis, which are at an angle of 120 degree, as we have established with a in case of trigonal crystal system. This also remains valid in the hexagonal crystal system here. So, the atomic density and the concentration of the atoms along A1, A2 and A3 is the same. So, that is why they have the same unit cell length here, and this is unequal with the C crystallographic axis here. And this also you can explain this in the with the same analogy if you use the 622 here. And for all the point groups of symmetry for the hexagonal crystal system, I have marked the A1, A2 and A3 axis and also vertical C crystallographic axis. So, in nutshell, in trigonal and hexagonal crystal system, you have 4 axes. The vertical axis is C, and in the horizontal plane you have 3 axes A1, A2 and A3, and their angle is 120 degree and they are equal in length, but they are not equal to the length of the C crystallographic axis. And this is in nutshell the orientation of the different crystallographic axes in the hexagonal system. So, this is the one where you can see that in these 2 cases here, that you have here, these are the different crystal faces here, and in this case A1, A2 and A3, the positive direction of A2, this is the negative direction of A3, this is the positive direction of A1. So, this essentially passes through the center of the edges of these two crystal faces here. Whereas, in this case A1, A2 and A3, they are perpendicular to these crystal faces. All these crystal faces are related to each other by the operation of this vertical 6-fold axisymmetry. And in case of the trigonal crystal system, the rhombohedral subdivision. So, this C crystallographic axis will pass through this, and you have the A1 in this direction, A2 in this direction, and the negative direction of A3 is in this direction. Now, let us come to this isometric crystal system here. So, in the isometric crystal system, there are 5 point groups here. What they are? 4, 3, 2, 2, 3, bar 4, 3 m, 2 over m bar 3 and 4 over m bar 3 2 over m. What is the minimum criteria? The minimum criterion for an isometric crystal system is the presence of 4 triad or 4 bar 3 axis, and there will be 3 crystallographic axes there, A, B, C, and A is equal to B is equal to C, and that is why we call it this axis as A1 axis, A2 axis and A3 axis. One of them is vertical and the other two are horizontal, and A1 angle A2 angle A3 is equal to 90 degree, and they are all equal in length, as I have just told you. A1 is equal to A2 is equal to A3. So, I give you an example with one point group of symmetry, let us say 4 3 2. You remember, you can recapitulate what 4 3 2 means. There are 3 4-fold axisymmetry. One is vertically oriented, that is this position here. The vertical direction is now given the symbol of A3 axis, which is projected on this plane of drawing as the center of this circle here. Whereas, your A1 where is the other direction here. So, another 4-fold axis of this horizontal 4-fold axis, another horizontal 4-fold axis, these are the directions of A1 and A2. The question is that why this A1, A2 and A3 are equivalent? These are equivalent essentially because that this direction, this A1 direction, if you can think of the presence of this 3-fold axis of symmetry here. So, you see this line, this curved line and this curved line produces 6 quadrants here, 1, 2, 3, 4, 5, 6. So, angle between this curvature and this curvature is 120 degree. Angle between this curvature and this line here, this is also 120 degree and this is 120. So, what happens here is that if you have this inclined 3-fold axis, it can rotate A1 and make it coincide with A2, and it also another 120 degree rotation, it makes coincide with A2 with the A3 axis here. So, this 120 degree, 120 degree and 120 degree. So, all these 3 directions then becomes equivalent here, and because you have the 3-fold axis of symmetry, the 3-fold axis of symmetry is present in every crystal class of the isometric crystal system. Everywhere you can employ this technique, so that A1 is equal to A2 is equal to A3, and the angle between A1 and A2 and A3 is 90 degree. Only there is a difference between the crystallographic axes that are present in the 5 point groups under isometric crystal system. In case of 4 3 2, the crystallographic axis coincides with the 4-fold axis, one vertical and 2 horizontal. In case of 2 3, the crystallographic axis coincides with the 3 2-fold axis symmetry, one vertical and the other 2 horizontal. In case of bar 4 3 m, the crystallographic axis A1, A2 and A3 coincides with the 3 bar 3 axis. In case of 2 over m bar 3, this coincides with this 3 2-fold axis of symmetry, and in case of 4 over m bar 3 2 over m, it coincides with the 3 4-fold axis of symmetry here. So, with this I show you how the minimum criteria, what are the basic criteria that are to be used for coining a particular crystal system and how the different crystal classes can be allocated under these different crystal systems here. So, this is in nutshell the different types of crystals under the isometric crystal system. So, this is a very simple one here, where A1, A2 and A3 can be oriented in a cube, which is perpendicular to this crystal faces, the 6 crystal faces in the cube, and this is an octahedron here, and this is the orientation of A1, A2 and A3, and this is a dodecahedron here. So, where A1, A2, for example, A1 that passes through the center of intersection of these 4 faces here, and same way these 4 faces they intersect at this point from the center. If we join, this is the position of A2 axis here, and you will be later finding that this is the position of the emergence of the threefold axisymmetry, because there are 3 faces here 1, 2 and 3. So, there is an angle of 120 degree here, and this is a crystal under the isometric crystal system, where all the 3 varieties of cube, octahedron and dodecahedron they are present here, and we will discuss in some details when we will be studying crystal forms. Now, let us consider that this particular basic criteria that we have developed can we see in some more details. So, let us have this flow chart here. So, I apologize, this is the letter is very small, but nevertheless let us consider is that does it have a 6-fold axis? If it is yes, so then you have an hexagonal crystal system here, and under this hexagonal crystal system these point groups can be linked here. Now, you also have, does it have a 3-fold axisymmetry? If it is yes, so does it have more than one 3-fold axis? So, if it is no, then you will have, if it is only one 3-fold axisymmetry, then you will be the trigonal crystal system, and under this you have this bar 6, that is 3 over m, or bar 6 m 2, 3 bar 3, 3 to 3 m and bar 3 2 over m, this will come. If there is more than one 3-fold axisymmetry, if it is present, fold axisymmetry, if it is yes, then this is the orthorhombic crystal system here. And if there is 3 perpendicular 2-fold axis, if it is the answer is no, then the next question is that does it have one 2-fold axis? Then there are 3 possibilities. If it is yes, then it has 2 different perpendicular mirrors parallel to the 2-fold axis. So, this will be your orthorhombic crystal system. So, we have 2 mm that we have learned. If it has a bar 4 axis, which is some form of 2-fold axis, then this will be a tetragonal system, which is we call it as bar 4 and bar 4 2m. And if it lacks a bar 4 axis and also lacks a mirror parallel to the 2-fold axis, then it will be the monoclinic crystal system, and we call it as 2 and 2 over m. And it's if it is does it have a mirror? If it is a mirror, then we have a monoclinic crystal system M, and if it does not have a mirror, then you have the triclinic crystal system, and we have 1 and bar 1. So, this is a very nice flow chart, and if you go through it, and then it will be able, you will be able to relate with each other that what are the queries here and how each query and answer will lead to the different combinations of crystal classes and the different crystal systems here. And here under the different crystal systems, what are the common minerals that are present, that names have been given here. So, in cube you have pyrite, you have garnet, and you also have halite and spinel. Under the tetragonal crystal system, apophyllite, rutile, zircon and wulfenite, these are the common minerals under the tetragonal crystal system. And in orthorhombic, the examples are barite, olivine, topaz and sulfur. And in case of hexagonal, you can think of corundum and quartz. In case of rhombohedral crystal system or trigonal crystal system, you have ilmenite and calcite. In case of monoclinic crystal system, so we have diopside, we have gypsum, we have epidote and we have orthoclase. And in case of triclinic crystal system, we have albite, blustonite, kyanite and rhodonite, and we also have studied microcline in the triclinic crystal system. When we discuss the crystallographic orientation, I have shown you that microcline, a variety of potash feldspar, also comes under the triclinic crystal system here. So, with this we come to an end to this particular 32 crystal classes and also the crystals, the crystal systems, the nomenclature and also how the different crystal classes or point groups of symmetry can be allocated under the different crystal system. So, once we have learned this, I will ask my students to have this class test. I will call it class test 1, and in that I have asked 10 questions, and this is a class test of around 55 minutes and the total marks is 60. And what you have here is that I read out the important questions that I have asked here in this class test. The first one is that state the value of the angle between the two-fold axis of symmetry and the mirror plane in bar 6 to M point group, and a mark of 1 that has been allocated here. The next question is that under this there are 5 questions here and each question carries 2 marks. So, a total of 10 marks are there under the question 2. The first thing is that what will be the point group of symmetry when there are 6 horizontal two-fold axes each at an angle of 30 degree. You have to name the name of the point group of symmetry. Number B, if 3 orthogonal bar 4 axes are combined with 6 mirror planes, 2 vertical and 6 inclined, what will be the name of the point group of symmetry? Third one, if there are 3 vertical mirror planes are combined with 3 horizontal two-fold axes at right angles to the mirror planes, what will be the name of the point group of symmetry? Under 4, that is D, if there are 2 vertical mirror planes of orthogonal orientations are bisected by 2 horizontal two-fold axes, what will be the name of this point group of symmetry? And finally, in E, there is 1 vertical 6-fold axis and this is combined with 6 mirror planes each at an angle of 30 degree and there is a center of symmetry. What will be the name of the point group of symmetry? So, what we have learned, so if you have gone through that the 32 point groups that we have generated by making certain assumptions and we have drawn with a circle here with some motifs, and for each 32 point groups you will find out that the orientations of axis symmetry, orientations of mirror planes and the presence or absence of center of symmetry is marked. And if you understood it, then any combination of this rotation axis, mirror planes or center of symmetry, you will be able to exactly locate the concerned point group of symmetry. So, I will request all of you to carefully study these 32 point groups, so that you will be able to solve this particular question here. In question 3, which one of the following combinations of rotation axis is an incorrect combination? So, I have given 4 combinations of rotation axis, that is 3 2 2, 2 3 3, 4 2 2 and 4 3 3. Which one of these is an incorrect combination? And you have to justify. There is very brief justification you have to give, and there are 2 marks that have been allocated to this question here. And in question 4, identify the crystal system in which the following point groups belong. What they are? Also find out the number of symmetry elements and their angular relationship. So, I have given 3 point groups of symmetry with the names 2 over m bar 3, 4 over m, 2 over m, 2 over m and 4 over m bar 3, 2 over m. So, what I have asked you? I have asked you to identify the crystal system in which this individual point group belongs to, and also I have asked you to find out the number of symmetry elements that are present in each crystal class and what is their angular relationship between these symmetry elements that are present here. And under question number 5, so in this there are 3 point groups of symmetry. For each there are 4 marks. So, there are 12 marks that have been given here. And in question number 5, state the value of the angles between the different axes of symmetry in the crystal class 2, 3. So, you have to tell us about the angle between the two-fold axis of symmetry amongst themselves, the angle between two-fold axis and three-fold axis of symmetry, and also angle between three-fold axis and three-fold axis of symmetry, and that is a 2 marks is given here. In question 6, state the value of the angles between the different axes of symmetry in the crystal class here. So, this is the same question that has been repeated here. So, you can ignore this particular question here. Then you have to name. So, this question will be, the sixth question will be this one here. Name the point group of symmetry in hexagonal, tetragonal, trigonal and orthorhombic crystal system that is produced by a combination of rotation axis, and you also arrange them in order of increasing symmetry. So, what I have been asked? You have been told that the point group of symmetry in hexagonal, tetragonal, trigonal and orthorhombic crystal system in crystal system that is produced by a combination of rotation axis. So, you have to identify them. So, only the rotation axis, and you have to arrange them in order of increasing symmetry. So, instruction here is that each wrong answer under this question 6a, this will have a carry of 1 negative marking or 0.5 marks negative marking, and for B it will be 1 negative mark. The next question is name the point group of symmetry in trigonal, isometric, orthorhombic and monoclinic tetragonal and hexagonal crystal system that is produced by a combination of rotation axis, mirror and center of symmetry. So, here also there is the instruction that negative marking will be there, 1 negative marking will be there, and there is a 9 into 2, there are 18 marks are there. And then you have to name the enantiomorphic point group of symmetry in a crystal system where there are 4 triads present. You also have to name the polar point groups of symmetry in a crystal system with the following crystallographic conditions, where A is equal to B is not equal to C and A angle B angle C is equal to 90 degree. And the final question is that name the point group of symmetry which does not belong to any one of the 3 groups, namely polar point group, centrosymmetric point group and enantiomorphic point group. And you have a 5 marks here. The instruction is that each wrong answer will have a negative marking of 1 mark. So, I would encourage all of you to practice on your own, and at some stage I will share with you the model answer, so that you will be able to find out that how much marks you have been able to score with this test 1. So, with this I conclude this first part of the crystallography, where I have discussed about the development of 32 crystal classes and also the crystal systems, and also how these crystal classes can be allocated under the 7 crystal systems. So, in the next lecture I will tell you about the nomenclature of crystal phase, the nomenclature of direction, the concept of zone axis and also zone symbol. We will discuss this in the next lecture here. Thank you.